Wow. A little learning is a dangerous thing. A little learning may lead us to believe that we understand things way beyond our comprehension. Great learning is even more dangerous. Great learning opens the door to possibilities and choices, and with choices comes responsibility. Not always a character trait of the human race. No amount of learning is as dangerous and as destructive as ignorance. Certainly, information can be used for good or for evil, but so can ignorance, and ignorance leaves us blind. We are here to listen to the 2025 Nobel Lectures, 9 laureates of great learning, 9 dangerous men. It sounds like the title of a Western movie, doesn't it? I look forward to seeing them all riding off into the sunset to the music of the great master Ennio Morricone. Like the heroes of classical westerns, you are indeed armed and dangerous. Armed not with 6 shooters, but with great learning, ready to do battle with the ultimate dangers facing humanity. Disinformation, alternative truths, and chaos. Darkness is strong and will prevail in the absence of light, and while it takes only a single candle to light up the darkest room, a lone candle may easily go out. This is why science is important, but teaching is paramount. Working in research is to learn. Communicating research is to teach. Research without teaching is hiding your light under a bushel. Light should be shared. Gathering and multiplying light leads to enlightenment, and enlightenment, as opposed to mere light, is robust. When Alfred Nobel planned for the conferment of the prizes that bear his name, the Nobel Lectures were an integral part of them. In these times of war and climate crisis, when truth itself is under attack, we have more cause than ever to feel gratitude towards Alfred Nobel for his vision to celebrate knowledge, light, and enlightenment. Perfectly aligned with the greatest benefit to mankind, this year's prizes are indeed eminently useful. The prizes in physics and economic sciences celebrate how that which is useful and small can be grown large. The prize in chemistry goes one step further to reveal that there are uses of that which isn't even there. To our laureates in physics, chemistry, and economic sciences, I extend my heartfelt gratitude that you have braved the inconveniences of travel to come to this Ultima Thule at the very edge of the world, to bring light at a time when that is in short supply. Thank you for your willingness to teach. I also want to thank all of you here who have come to listen in this hall and online for your willingness to participate in Alfred Nobel's dream about enlightenment. Thank you for your willingness to learn. In the darkness of our Nordic winter, bring it on. Let there be light. Fiat lux. I now invite Ola Eriksson, Chair of the Nobel Committee for Physics, to introduce this year's laureates in physics.
Good morning, ladies and gentlemen. You are all accustomed to, in your everyday life, what you see on the screen behind me. On your left, you see a boy throwing a ball onto a wall and it bounces back. And you know in your everyday experience that the picture to the right just doesn't happen, not in the world of classical physics. The ball never ever goes through a forbidden region. In the microcosmos, that of atoms and electrons, this is everyday life experience, and there's no problem with this at all. Alpha decay from the atomic nucleus is one such example. In the early 1980s, late 70s, researchers started to think about if it is possible to also see the quantum mechanical tunneling that is so well known from the microcosmos, if that was also possible in the macrocosmos for macroscopic objects. And it was identified that the most suitable object to investigate such an effect in was that of electrons in a conductor forming a superconducting state. So in the top graph, you see electrons in a normal state in a normal conductor, copper wire, as an example. In the middle panel, you see the superconducting state where electrons pair up and they're holding hands. Those little spherical objects have now paired up into what is known as a Cooper pair. And at very low temperatures, they form a superconducting ground state, the Bose-Einstein condensate, that has no distinguishability between Cooper pairs. They are all in one big macroscopic object. So this was then investigated to investigate and see if the laws and the discoveries and the phenomena of quantum physics and quantum mechanics could also be seen in macroscopic objects. And a macroscopic object of this kind can be trapped into a potential well, and that's the figure you see on the right. You have the energy of the well on the y-axis, and you have the position on the x-axis. You can imagine this would be you hiking around in the Swedish mountains, and you're in a valley, and you want to come out of this valley, and you cannot tunnel through it. You have to hike above the peak. But in the world of superconducting macroscopic phenomena, this was not quite the case, and the tunneling phenomenon was discovered and described by this year's laureates. And the smoking gun experiment that proved this, that proved the tunneling phenomenon, that is what you see on the left-hand side here. You see the escape rate of this object on the y-axis, and you see its position. That would be your position if you're hiking around in the Swedish mountains on the x-axis. And if the classical world would prevail and describe the rate with which this object would climb out of this well, it would follow the straight line that you see on the left plot. But at low enough temperatures, quantum effects start to play a role, and the curves deviate from the straight line, and this is the smoking gun experiment that demonstrated quantum phenomena of a macroscopic object. You will hear more about this in a second. But first, let me read to you the motivation to this year's Nobel laureates. To John Clarke, University of California, USA, Berkeley. Michel Devoret, Yale University, University of California, USA, and Google Quantum AI. And John Martinis, University of California, and Qolab, USA. For the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. So please join me now in welcoming the first speaker of our trio of speakers to the stage to give his presentation. You want to sit down? Good.
From SLUGs to macroscopic quantum phenomena. I would like to talk about this subject in two separate episodes. The first is my work at the Cambridge University, where this was really the ultimate route why I ended up at UC Berkeley. So I will begin with an overview of the work I did many, many years ago at Berkeley. And I'm sorry, I will begin with talking about my work at Cambridge University, and then I will move on to talk about my research at UC Berkeley, which talks about three topics: macroscopic variable, energy level quantization, and macroscopic quantum tunneling. So let me start out by talking about my research at Cambridge. I was a graduate student at the Royal Society Modern Laboratory on Free School Lane in Cambridge. And there's a more recent photograph of me. My thesis advisor was Brian Pippard as of the 1st of October, 1964. And he set me a rather tough project. He wanted me to be able to measure voltages as small as 10 to minus 12 or 10 to minus 13 volts at a time when the state of the art was 10 to minus 9 volts. Well, I pondered this for a while, and I thought that's going to be a difficult experiment. But a little bit later, Brian Josephson gave a colloquium explaining Josephson tunneling. And this really changed my world, and to be honest, the world of many other people. But he spent quite a lot of time talking about various topics, and one of the ones he talked about was flux quantization. And the basic idea there is that if you have a superconducting ring in which there is superconducting magnetic flux, then the flux is quantized in units of the flux quantum, phi 0, which is equal to Planck's constant over 2e. Of course, he talked about Josephson tunneling, and the basic idea there is that you first of all deposit a thin film of superconductor on an insulating substrate. You then oxidize it, and then you deposit a second film. And that's the basic principle of the Josephson junction. But he went into this in considerably more detail. And on the top left-hand side here, whoops, we see an insulating barrier, which is, an insulating barrier which separates two superconductors, and the Cooper pairs, which are what makes superconductors superconducting, are able to tunnel through this barrier. And on the right-hand side, you see the plot from the very first observation experimentally of Josephson tunneling by Anderson Rowell at Bell Labs. And what you see on the vertical axis is the current versus the voltage on the horizontal axis. And at very low currents, no voltage appears, but as you increase the current sufficiently, then you get a transition to the voltage state. And this depends actually on the magnetic field that one is applying. Well, Brian Josephson worked out the two very short equations that explain all this, and they're written here. The first is the current I through the junction, and that's equal to I0 sine delta, where I0 is the maximum supercurrent, or the critical current, and delta is the phase difference across the barrier. In the voltage state, the delta by dt can be written as 2 pi times the voltage divided by the flux quantum. And he did this remarkably in his very first year as a graduate student at Cambridge, and he won the Nobel Prize in 1993. Another very important development that happened just 1 year later, in 1964, was by Jekyll, Lamb, Silver, and Mersereau. And they came up with the idea of the SQUID, the Superconducting Quantum Interference Device. And the basic idea is that you have a superconducting ring interrupted by 2 Josephson junctions. And remarkably, if you start to change the magnetic flux in the loop, then the critical current oscillates as a function of that flux, and the period is phi 0, the flux quantum once again. So the SQUID unites the 2 ideas of Josephson tunneling and flux quantization. And this is on the right, a figure of the device that they made, and at the bottom you see there's a superconducting film, and then on top of that there's a rather thick layer of insulator, and then at each end of that is a Josephson junction. And the plots here are of the Josephson current versus the magnetic field. And if you look here, you see that as you change the magnetic field, there is these oscillations in the critical current. Well, the very next day, my thesis advisor, Brian Pippard, came into my office and he said, "John, how would you like a voltmeter with a resolution of 2 × 10⁻15 volts in 1 second?" And I thought, that would be amazing. But then he explained how you would do this. And here is what he drew on the blackboard. And on the right-hand side, you see a SQUID. And then the inductance of the loop is L, and it's coupled to another inductance with the same inductance L in series with a resistor, so that if you apply a voltage across this input circuit, then you couple flux into the SQUID. And just for simplicity, he said, let's make L equal to M. And basically, that's a digital voltmeter. And the voltage resolution is given by V input, which is equal to I phi 0 times R, and that's the amount of current you have to apply to get 1 flux quantum in the loop. And if you choose a time constant of 1 second, then you find that the actual resolution is 2 × 10⁻15 volts. And that was quite remarkable at the time. It would represent a 6 order of magnitude improvement in the state of the art. However, there was a problem. The modern laboratory did not possess the equipment to deposit thin films. And so I couldn't make a device that replicated the kind of device that had been made in the US at the time. And I spent several weeks trying to fabricate a Josephson junction from pieces of niobium foil and niobium wire, sometimes soldered together with lead tin solder, and none of my attempts was successful. Fortunately, my problem was solved one day during our daily tea break, when I was expressing my frustration at not being able to make a Josephson junction. And Paul Raitt, who I remember very well still, a fellow research student, pointed out that niobium has a surface oxide layer, and lead tin solder is a superconducting wire. Why don't you put a blob of solder on a piece of niobium wire? And he was suggesting a device that looks like what's on the left-hand side here. And you can see that there is a niobium wire, and I've put a blob of solder on it, as you can see here. Then there are two leads so that we can measure the current voltage characteristics. And before dinner, and then I put the device in my cryostat with some liquid helium, and before dinner, that's what we saw. So once again, we have current on the vertical axis and voltage on the horizontal axis. And what you see is that at low currents, there is no voltage, and then when you increase the voltage sufficiently, then you have a voltage developed. So that was, for me, the beginning of how to make a Josephson junction. The day after, I put this device on my desk, and when Brian Pippard came in the morning, he said, "It looks as though a slug crawled through the window last night and expired on your desk." And so here's a photograph of a slug. So anyway, that decided the name of this device. And so the slug was the superconducting low inductance undulatory galvanometer. And so if you now look at this figure here, you find that the slug has an extraordinary property, that when you change the current flowing along the niobium wire, the voltage across the slug oscillates as a function of this bias current. So quite remarkably, the slug behaves as though it were a squid. And this enabled me to make an analog voltmeter with a voltage noise of 10 to the minus 14 volts per root hertz. And so this was still in my first few months of being a graduate student. So I spent a great deal of time after that trying to improve the slug, but also doing a variety of experiments that could only be done if you had a sensitivity of this kind. Well, after years went by, I started to ponder about what I should be doing next. And a little while before I graduated, Paul Richards, who at the time was a faculty member of the physics department at UC Berkeley, came to visit my lab. And he was curious to see what I was doing, and also I would like to hear what he was doing for his research. And I really enjoyed meeting him. So, as I said, I was pondering what to do next. It occurred to me that as a postdoctoral scholar, it will be a very interesting trip to the US to go to UC Berkeley, where Paul was a graduate student, was a faculty member. He was a wonderful mentor for me, and he and his family became my close friends. Very sadly, he's no longer with us. So on January the 6th, 1968, I moved to the physics department at the University of California as a postdoc for a year. And I worked away at my slugs again and various applications that you could do with them. And they then invited me to become a faculty member and also at the same time a senior scientist at Lawrence Berkeley National Laboratory. And then I started my research group. Sorry. I think I may need some help here. Sorry for the little hiccup. So, I, at some point, took on a variety of graduate students and postdocs. And in 1980, John Martinis, who had just received his bachelor's degree at Berkeley, joined my group as a graduate student. And in 1982, Michel Devoret, who had just received his PhD in France from the University of Orsay, joined my group as a postdoctoral scholar. We had to figure out what we'd like to work on, and at the time there was a very interesting paper and discussion by Tony Leggett, Do Macroscopic Variables Obey Quantum Mechanics? We decided to investigate his intriguing question using a current-biased Josephson junction. And the macroscopic variable is the phase difference delta between the superconducting order parameters on either side of the barrier. So we realized that we had to cool our device to very low temperatures, and so we built a dilution refrigerator, and the bottom end is shown here. And this enabled us to get down to temperatures of, say, 18 millikelvin. We also invested a great deal of time to minimize the level of electrical and magnetic noise in the device. And the actual superconducting circuit is at the... I'm sorry. Sorry, I don't know what's happened here. And the superconducting device is at the bottom here. So, after our first year or two of work, we published our first paper, our physical review letters, Energy Level Quantization in the Zero Voltage State of a Current-Biased Josephson Junction. And let me basically give a brief overview of what that's about. And in this part of the talk, I won't go into any details about what's actually how we work the calculations out. But on the left, we see a qubit potential U versus the phase difference delta, in which there are 3 energy levels. And on the right-hand side, we see the circuit diagram. Here's the junction, shunted by a resistance and a capacitance. You could apply microwaves, and you could apply a bias current, and you could measure the voltage. And the plasma frequency of a device like this is given by this equation, which I won't explain, where phi 0 is the flux quantum. And we can control the energy levels by adjusting the bias current I. Well, the first thing that we discovered was that if we apply microwaves, then the escape rate can be enhanced. And the escape rate gamma out of the well in the presence of microwaves of power P is resonantly enhanced over that in the absence of microwaves when the microwave frequency corresponds to the spacing between 2 energy levels. And the change in the escape rate is given by gamma P minus gamma 0 over gamma 0. So we start to investigate various properties, and here I'm showing the escape rate versus the bias current. And this is a plot of our parameter gamma P minus gamma 0 over gamma 0 in the presence of 2.2 gigahertz microwaves. And what we see is, if we look at the result of doing this, is that we can observe 3 peaks, and these correspond to transitions shown above. For example, the right-hand one is the 0 to 1 transition, which is the right-hand peak. Here is the 1 to 2, and here is the 2 to 3. And so these peaks get sort of weaker as you go to these higher transition levels. And then the lower plot is the calculated energy level spacings of the transition from the n state to the n+1 state versus the bias current. And here, for example, is the 0 to 1 transition. Here's the 1 to 2, 2 to 3. And the dotted lines here indicate the values, indicate the errors in the critical current and the capacitance. And the arrows here indicate which transition we're looking at. Well, now let's look at the frequency, microwave frequency dependence. And in the top curve, that is A, we're looking at gamma p minus gamma 0 over gamma 0 versus the bias current in the presence of 4 different microwave frequencies, which are labeled here. And in B, we're looking at the calculated energy level spacings versus the current bias. So these are the different spacing levels, and the arrows indicate the values of bias current at which resonances are predicted. The dashed line out here is the plasma frequency. The shift in the positions of resonances as the microwave frequency is changed is in excellent agreement with the predictions. Well, another thing that interested us is the evolution from quantum to classical behavior. And at the lowest temperature, that's the bottom plot here, we see a single resonance. As we increase the temperature, which is measured here in terms of k Boltzmann T over h bar omega, the frequency, what we see is that an additional shoulder begins to appear, and at the highest frequency, A, the response is a continuum, and that implies that we are looking at classical behavior. So to summarize this first paper, we observed microwave-induced resonances, resonant enhancement of the rate at which current-biased Josephson tunnel junctions escape from the zero voltage state. The positions of these resonances are in excellent agreement with the predictions of a model in which the energy levels are quantized with no fitting parameters. These results provide very strong evidence for the quantum behavior of the macroscopic variable delta. Well, now let's move on to our second paper, which was published just 3 weeks later. Measurements of macroscopic quantum tunneling out of the zero voltage state of a current-biased Josephson junction. So once again, I will go through this paper and mostly focus on showing the figures, and some of the details like this I won't take the trouble or won't have the time to go through. But just to summarize a couple of things, in the thermal regime, meaning k Boltzmann T much greater than h bar omega plasma, the particle escapes from the well via what's called thermal activation. So it's a thermal process, and the equations are written here. On the other hand, in the quantum regime, k Boltzmann T much less than h bar omega plasma, the escape is predicted to occur via macroscopic quantum tunneling at a rate that, again, we calculated. And the only number I'll mention here is that the crossover temperature at which the energy rate changes from thermal temperature dependent to quantum temperature independent is predicted to be h bar omega plasma over 2 pi k Boltzmann in the limit q much greater than 1. And Q is the damping factor, omega plasma times RC. Well, it turns out that a very useful and important characterization of all this is the escape temperature T sub ESC. And to express the experimental measurements of the escape rate in a way that is independent as possible of the parameters of the junction, we introduce the escape temperature, T escape. And that is defined through the result I've shown here. In the thermal regime, we have one prediction, which involves the parameters here. And in the quantum regime, at T equal to 0, the prediction is again given by this complicated equation. And the crossover temperature at which the escape rate changes from thermal, meaning temperature dependent, to quantum, temperature independent, is predicted to be h bar omega plasma over 2 pi k Boltzmann in the limit q much greater than 1. Well, here's another plot which you also saw a little while ago. And this is T escape versus temperature for two values of critical current. And there is the so-called quantum junction, which has a relatively high critical current. And, I'm sorry. Oh, I'm really sorry. This thing is driving me crazy. So the quantum junction is one with a relatively high critical current, and the classical junction has a much lower critical current. And the two arrows here for the solid arrow represents the predicted crossover temperature for the higher critical current, and the open arrow here is for the lower critical current. The predicted value of the escape rate, which is plotted here versus temperature, is indicated here on the left with this little symbol here. And what you see is it lines up really rather accurately with the bottom end of the quantum plot. And the lower temperature value of the T escape are in good agreement with the T equal to 0 predictions shown here. So this was a very important result. And what we've finally wanted to end up with is the dependence of the escape temperature on the bias current I. And I show the results here at two different temperatures. In the upper figure A, at 151 millikelvin, we're in the classical regime, and T escape decreases with the increasing bias current. The lower plot shows the result at much lower temperatures. And what you see here is that the T escape increases as you increase the bias current. And within the experimental uncertainties, the data are in good agreement with the theory. The very different dependence of T escape on the bias current in A and B demonstrates that the escape mechanisms are different in the classical and quantum regimes. So, in summary, we measured the escape rate of a current-biased Josephson junction from the zero-voltage state for two values of critical current. For the lower critical current, T escape followed the classical prediction to within experimental error. For the higher critical current, T escape was equal to T at higher temperatures that began to flatten off at temperatures below 50 millikelvin, becoming temperature independent 25 millikelvin. Within the experimental uncertainties, the low temperature value of T escape was in excellent agreement with the zero temperature theoretical prediction for macroscopic quantum tunneling with all relevant parameters measured in situ in the classical limit. The combined results, the combination of the result from these two publications provided very strong evidence for the existence of energy quantization and macroscopic tunneling in an electrical circuit. For this work, as you know, we were very privileged to receive the Nobel Prize, and the citation was for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. And in conclusion, I would just like to note that there were various other groups also working on macroscopic quantum tunneling who also made very important contributions. So thank you very much for listening. Oh.
So thank you very much, Professor Clarke, for a wonderful presentation. Our next speaker is Michel Devoret, born 1953 in Paris, France. He received his PhD in 1982 from Orsay University, as you heard in a few seconds ago. He's now professor at Yale University, New Haven, also at Santa Barbara, UC California, and is also at Google Quantum AI USA. So please join me in welcoming Michel Devoret to the stage.
Thank you. Try it. See. It's bizarre. Maybe it's going. Okay. Good morning. It is a great honor to give this lecture in front of distinguished colleagues and friends, and also my close family. I would like also to thank the Swedish Academy of Science and the Nobel Foundation for this prestigious award. I feel actually doubly honored because, as you know, this is the 100th anniversary of quantum mechanics. Quantum mechanics is counterintuitive. Its logic is very different from the logic we experience in our everyday life. When I started my PhD, I actually applied quantum mechanics to a simple molecule, the hydrogen molecule. But like this character that you see on the right of this slide, my life took a new turn when I did a postdoc in John Clarke's lab 40 years ago. And with John Martinis, who was a graduate student at the time, and John, we started an experiment that was a test of how variables like currents and voltage, how does quantum mechanics work for these variables. And for me, this was a lucky break. I had dreamed for many years to work on the foundations of quantum mechanics. I was inspired by the work of Alain Aspect, who defended, and I had the pleasure of being there in the audience when he defended his thesis in the mid-70s, and the room was packed. So quantum mechanics at the macroscopic scale is not something that was completely new at the time of our experiment. Actually, you could hear about it in popular books that try to convey quantum mechanics to a large audience. But this quantum mechanics at the macroscopic scale was essentially in the form of thought experiment. And here I'm going to give you an example which was invented by George Gamow, who wrote this wonderful book, Mr. Tompkins Explores the Atom. So George Gamow actually, very quickly after the discovery of quantum mechanics, explained alpha decay, alpha radioactivity, by considering the following idea. So on the left of the slide, there's a reminder that tells you what is radioactive alpha decay. If you take, for instance, the atom of uranium, and you consider its nucleus, after a certain time, it's going to decay into thorium and emit an alpha particle, which is actually a helium atom, or something you can describe also as 2 protons and 2 neutrons. So this alpha particle is, in the words of Gamow, it is transposed into a marble on the diagram on the right. And this marble starts in a sort of molehill with a crater in the middle. And when the marble is at rest, classically, it cannot escape. Its escape would mean that energy would not be conserved. You have a hill to go up and down to escape. But quantum mechanically, this marble can borrow energy. Can borrow energy from what I would call the Planck bank, which specifies that you can borrow a certain amount of energy during a small amount of time. Actually, this is given by the Planck's constant, and this Planck constant tells you that you can borrow during 1 second 10⁻34 joules, or during 1 nanosecond, 10 to the minus 25 joules. And we're going to see that 10 to the minus 25 joule is actually a manageable quantity. So, so this particle escapes, and why does it escape? Well, the crater corresponds to the attractive interaction of the alpha particle inside the nucleus due to the strong force. So this is why you have a dip. But outside, the alpha particle, which is charged positively, is repelled by the nucleus and hence the downward slope. And so this potential is the description by Gamow of alpha decay. And you see that Gamow, in fact, has no doubt if the marble would be sufficiently light, well, you should observe this effect. If you take a dog bowl at home and a marble, you should see this, provided, of course, that the marble is sufficiently light. Now, Tony Leggett, in the mid-80s, says, wait a minute, actually, we have absolutely no evidence that quantum mechanics works at the macroscopic scale of marbles. In fact, Tony Leggett was well placed to say that, because even though people at the time were saying that superfluidity or superconductivity are phenomena that display quantum mechanics on the macroscopic scale, in fact, he knew that in such phenomena, quantum correlations are actually deployed on a very small scale, and the order propagates at the macroscopic scale by completely classical interactions. So Tony Leggett is essentially proposing experimentalists to try to see if you can make a cat in the superposition of being dead and alive at the same time. And in proposing this to experimentalists, he is really interested in measurements. What happened in a measurement when the superposition is actually changing, the measurement is changing an end into an or. You have only one outcome. The cat is either dead or alive when you make a measurement. Now, of course, Tony Leggett had a very special cat in mind. Instead of taking a live cat, he was thinking about an electrical circuit. And on this picture, what you have is an oscillator, an electrical oscillator, which actually you have in your cell phone. It's made of aluminum. It's millimeter in size. And if you cool it to 20 millikelvin, which was the temperature of our experiment, all the electrons in this circuit are condensed and form one incompressible fluid that is going to move bodily in the circuit. To understand this idea of macroscopicness of the circuit, it's good to compare it to an atom. So I'm going to take a very simple atom, the hydrogen atom, and you have an electron which orbits around a proton there. And on the right, you have the equivalent system, but of course the dimensions are many, many orders of magnitude larger. You have this electrical circuit, which is a coil, an inductor shunted by a capacitor. And in that system, the electrons are going to move bodily from one plate of the capacitor to the other. So let's see what this motion is. This is OK. So you see the electron, classically, of course, in a classical picture, orbits around the proton. And what is happening in the circuit? So you see in the circuit, this whole incompressible fluid moves from one capacitor plate to the other by passing through the inductor. But at this low temperature, as you can see, suggested in this animation, there's no internal degree of freedom that is actually stimulated by this motion. So there's actually an analogy that you can draw. In the atom, you have a single electron. In the circuit, you have a whole superconducting condensate. And if you want, it is the center of mass of this condensate which is the analog of the position of the electron. The velocity of the electron is the current through the inductor. And the force on the electron, if you want to push the analogy, it would be the voltage on the capacitor. Okay. Now, there's a big difference, of course, and why do we say that this circuit is macroscopic? Well, from an application point of view, you can attach wires to a circuit, and therefore you can make two circuits, for instance, interact very strongly, or you can make a very strong measurement on the circuit, which is much more difficult to do on the atom. So that's why we are interested in demonstrating quantum mechanics at the level of circuit. Now, we have to test if this macroscopic object is really quantum. And Tony Leggett's hypothesis was that you could take the flux through the inductor of this circuit and consider it as a position, and the charge on the capacitor is the conjugate variable and can correspond to the momentum of a particle. And therefore, if you follow this idea, which is the equation in the bottom, then you expect that there will be quantized energy levels, as John mentioned in his talk. But this will happen essentially in any circuit. In the case of this inductor and capacitor, you have actually equidistant energy levels. What is really different from an atom in this circuit is that, for instance, if you take the transition frequency between levels, this transition frequency, as you can see in the formula that I have indicated on the right, this is determined by these two ingenerable quantities, which are the value of the inductance and the value of the capacitance, which you can change by changing the geometry. You cannot do this for actual atoms. You have 92 atoms in the periodic table, and that's it. Or if you want the equivalent of the L and the C here are fundamental constants like the electron charge and the mass, which are given once and for all. Here we can adapt the circuit to a particular function we are interested in. Now, macroscopic objects are submitted to a lot of friction in general. And for instance, in an electrical circuit, you may have some resistance across the capacitance and the inductance, and this has the effect of broadening the energy levels. And as you can imagine, if the dissipation is too large, the levels will be too broad, and all this quantization will disappear because the levels will overlap. So you have to be careful in controlling the dissipation. Can we can we take this circuit and put it in a quantum state? Yes, we can. We can actually use some residual dissipation. So dissipation is not completely bad. You need a little bit of it. And with this, you can reset the circuit, provided that the temperature of this dissipation is low enough. And the equation that John mentioned already is that the transition between levels, the energy between two consecutive levels, has to be greater than actually the energy of temperature fluctuation. And so you can see that for a circuit that you have in your cell phone, which is at a few gigahertz, in fact, H bar is not really that small if you have a dilution refrigerator, which really cools the resistance to a few tens of millikelvin. Okay, but at this point, Tony realized that there was really a problem. In fact, this LC circuit is a little bit too simple. It's when you stimulate it with some microwave radiation, what happens is that because all these levels are equidistant, you will stimulate all the transitions at the same time. And in fact, if you start from the ground state, you will end up with a state whose average will behave in a completely classical way. This is a problem. So we say, it is said in the quantum mechanics textbook that the harmonic oscillator is always in the correspondence limit. 40 years ago, this really was a problem. Today, there are ways of going around this. But you see, what we need is actually not a system with a parabolic potential, where transitions are degenerate. We need a system where the potential energy is anything but a parabola. The parabola is in dashed line in this diagram. You don't want that parabola. You want any potential that would flare up, for instance, as you go up in energy. In that case, all the transitions now are non-degenerate, and if, for instance, if you have this circuit at high temperature which emits radiation, it will emit this radiation in discrete lines. And so you can address now each transition separately. So if you shine microwave at a particular transition, you can go, for instance, from 0 to 1, from 1 to 2, and in this way address any quantum state. Now, there is something that really will determine how good will be the quality of your manipulation. You see, if you want to control this system, to manipulate it, there is something very important that you have to observe. You want nonlinearity, you want these lines to be separated, but friction is important, because what counts is the relative distance of two transitions relative to the width. So you need to have a good nonlinear system, but you also you need very small dissipation. And this was something that Tony Leggett realized. There is only one electrical element that provides this combination of very low dissipation. In fact, there's no known limit to the dissipation of a Josephson tunnel element, and enough nonlinearity. So, what does this junction, how you should think about this junction? You see in the schematic on the right of this picture here, I have represented the Josephson tunnel element, which replaces the inductor, by a cross. And the cross doesn't evoke at all an inductance, but the cross was chosen for historical reason. And if you follow John's talk, it should be pretty obvious why it should be a cross, but I won't go into this detail. Let's take this cross element, this Josephson tunnel element, and relate the current to a sort of flux. So this is what is called a generalized flux. You remember Faraday's law. The time derivative of a flux is a voltage. We can invert this relation and introduce the time integral of the voltage across the junction. And that creates a variable which is the equivalent of a flux. Now, if we... okay, so... okay, good. If we now plot the energy of this tunnel element as a function of this generalized flux, we do get something that deviates from a parabola. In fact, it deviates a lot. We get this cosine potential. And this cosine potential has a periodicity which is given by h bar over 2e. And why does E come into play here? It's because electrons tunnel one at a time across the junction. In the superconducting state, they tunnel as pairs, but what is important, what determines the shape of this potential, the periodicity, is the fact that charges goes one by one through the junction. Okay. Now, you see, in this potential, you will have non-equidistant energy levels, but of course, the fact that the potential is flat like this makes things actually quite difficult to measure. Actually, we could have done a specific heat measurement and resolve these levels, but this was 40 years ago, an extremely difficult experiment. So instead, what we do is that, or what we have done was to pass a bias current. So we have this current generator which passes a current through the junction, and this has the effect of tilting this cosine potential. Now, we have these levels, but they are metastable. If you populate one level, it will eventually decay because its wave function leaks into the barrier. There are two parameters that determine this potential, two very important parameters. There are this plasma frequency, omega sub p, which is the frequency of the small oscillations at the bottom of the well, and then there's this barrier height. It is absolutely crucial in the experiment to control these two parameters. And why? It's because actually there are two escape mechanisms. The state of the circuit, which is represented by this yellow ball here in the diagram, so that's the whole state of the circuit, it can escape from this well in two possible processes. The yellow process is a process in which the thermal excitation is going to help you go from one level to the next and so on until you go out of the barrier by the top. If you are in the regime where the temperature is sufficiently small and the crossover temperature is given by this ratio of the energy separation divided by K Boltzmann, then you will escape through the barrier by the tunneling corresponding to the purple arrow. And I hope that you recognize that the situation is similar to alpha decay. So our whole circuit is now the equivalent of a radioactive nucleus. How do we detect this, that, you know, the equivalent of radioactivity? Well, in this system, you see the whole state of the circuit changes. So on the left, the current, this bias current, can go through the tunnel element, through the cross, and that corresponds to this yellow particle, which corresponds to the state of the circuit. The particle is trapped. It can move in the well, but its average velocity is 0. That means that across the circuit, the voltage is 0. This is the 0 voltage state. You see that on the diagram, you have a resistance, and this resistance actually is something that we impose in the circuit. It corresponds to the voltmeter. The voltmeter is going to be the equivalent of the Geiger counter in radioactive decay. When the whole state of the circuit switches from the 0 voltage state to the non-zero voltage state, or in the slide here, it's just called the voltage state. There's a voltage that appears across the circuit, and we can detect it with our voltmeter. And why do we produce a voltage? Well, you see, as soon as the particle escapes, it rolls down this tilted potential. It picks up speed, and speed in our language is voltage. So by detecting this pulse of voltage, we know that the whole circuit has changed state. And this is the equivalent, the macroscopic equivalent of alpha decay. Now, I have to say something very important. There is two tunneling in this experiment. There is tunneling at the level of single electrons that go through the barrier, and that creates the Josephson effect. It creates the shape of the potential, and this tunneling has nothing to do with the switching of the entire circuit from one configuration of the currents into another. These two levels should not be confused. What we have discovered is that it's the tunneling of the state of the whole circuit, the tunneling of electrons and the tunneling of electrons in pair. That was the discovery of Josephson. So what we've done is post-Josephson physics. Okay. Now, John has shown a photo of our experiment. In this yellow box, we show exactly the shape of the junction. It's a junction that is actually lead indium junction, niobium lead junction, which has the merit of being superconducting at helium temperature, so we could check all the parameters in situ. These cylinders are actually filters, and they are very important, as John said. In this experiment, we narrow the bandwidth to kilohertz, and we have to filter out every other part of the spectrum. As I said, it was important to measure all the parameters of the system in situ. And in particular, this plasma frequency is very important to measure because it determines the crossover temperature. And an experiment that we did in the classical regime taught us that we could, if we measure the enhancement of tunneling, find this plasma frequency on the right edge of this resonance curve. And John has described our experiment. He has described our two papers. I'm not going to, in view of the time, I'm not going to repeat what he said. I will I think it's important to mention that 14 years later, colleagues at NEC, Yasunobu Nakamura, Yuri Pashkin, and Zhou Shen-Tsai, saw this superposition of the first and excited state, not in frequency domain, but in the time domain by doing this beautiful experiment on Rabi oscillation in the Cooper pair box. And Yasu is here in the audience, and it's great. On the right, so a few years later, we showed at Saclay that we could control this qubit not only on one axis, but on all axes. And you see also that the time scale is 3 orders of magnitude larger here. So coherence had been increased. Well, at this point, I am almost done. I see that I only have a few minutes left. So in that last few minutes, I just want to tell you that these previous experiments launched this new field of quantum superconducting circuits in which you have these 3 elements which can be combined to make artificial atoms, molecules, and even more complex circuits like quantum limited amplifiers. And I would like to acknowledge here all the people who are in the audience that have participated in this exploration. These artificial atoms have this analog of the Mendeleev table. I don't have time to comment, but each of these dots represent some configuration, some kind of new artificial atom. And there are two that are popular, the transmon and the fluxonium. And recently, by the way, this is an image of the transmon. And recently, I will have to rush here, but in the group of Nathalie de Leon and Andrew Hook at Princeton, the quality of these artificial atoms has been extended to a number which is basically that of the hydrogen atom. And what can you do with these artificial atoms? Well, you can do a certain number of experiments you cannot do with real atoms, and this is a list of these experiments. And finally, I would like to just say that this, as a perspective, this new field of artificial atomic physics and microwave quantum optics open new applications in quantum information processing and quantum sensing. And the question that is left is where can we extend, at what point can we extend quantum mechanics to macroscopic systems? This is still an ongoing question, even though we've pushed the scale at another level. And finally, since I have 0 minutes left, I would like to acknowledge all my colleagues with whom I have had this great privilege and great happiness in exploring these superconducting circuits over the last 40 years. And on this, I would like to thank you for your attention.
Thank you so much for this inspiring talk, Professor Devoret. The third speaker is already ready. I would like to welcome John Martinis. He was born 1958 in Los Angeles, USA, PhD 1987 from University of California. He is a professor at University of California, Santa Barbara, and Chief Technology Officer at QO And join me in welcoming Professor John Martinis.
Thank you. Thank you. Thank you. This is a great honor to speak to you today, and oh, what happened here? Back up. Oops. And great honor. As a graduate student, I joined John Clarke's group because he was doing at the time some really fascinating experiments looking at quantum noise phenomenon in these electrical circuits. And that kind of combined my personal interest, a hobby in electronics, as well as a graduate student where you're fascinated by quantum mechanics and you want to do experiments to understand it better. So today I have an honor to talk about our collaboration, but what turned out to be my thesis at UC Berkeley, and then talk a little bit about the end, where it's led, give some examples where it's led in my career with some other nice experiments. I want to say in my career I've been really privileged to focus on physics instrumentation, to make these quantum devices in a variety of form. And what I learned a few years ago by going to Cambridge, that if you look at my scientific family tree, if you like, through John Clarke and Cambridge, I have a very interesting sequence of graduate advisors who have done fantastic instrumentation and discovered a lot of physics from that instrumentation. So there was a real focus in John Clarke's group to do that I appreciate. Also at UC Berkeley, of course, there's Ernest Lawrence building the cyclotron and building all these accelerators at Berkeley, and that contributed to my interest in exploring such scientific instrumentation and led to many interesting things here. So we've talked before about macroscopic variables obeying quantum mechanics. I'm going to say my personal view, what is actually kind of discomforting to physicists with quantum mechanics, is there's actually two propositions in quantum mechanics. One has to do with the wave nature of quantum mechanics, and of course described by the Schrödinger wave equation and the energy levels and things like that. But a second part has to do with observation and measuring of that quantum state. And physicists really feel, a lot of physicists feel that there are one too many propositions in that. It should only be one. That's how we think. Of course, it works in the real world. You can do things. But part of this discomfort, I think, is very well described in the Schrödinger cat paradox, where you have a microscopic decay of atom, which either kills the atom or not, depending on whether it decayed. And then before you open the box to observe it to measurement, the paradox is, will this living being, a macroscopic cat, can be described as a dead plus alive state. And of course, as discussed before, Professor Leggett discussed that, well, maybe quantum mechanics is such that macroscopic objects can't be in a quantum superposition. We need to look for experimental evidence that that could be the case. And again, he proposed these electrical circuits. Now, one of the things Leggett did that was very nice is he said this is distinct from showing that microscopic quantum mechanics can be observable on a macroscopic scale. A good example of this are crystals, where you have atoms, because of the microscopic physics, attached to each other, and they'll stack up in a regular way because of that. And if you grow them right, they can stack up to macroscopic distances. But it's still, you're looking at a macroscopic property of them stacking up in a very reproducible way. And this is such a magical phenomenon that in my home state of California, such crystals are thought of having magical healing powers. So it's truly an amazing phenomenon. Now, the same thing happens with superconductivity, where the superconductors can kind of stack up in the phase, so you can get large superconducting coherence and the like. And what, of course, we're doing is something looking very different. Will a macroscopic object obey quantum mechanics? For example, throwing a ball against the wall, and okay, one small period of time, it'll tunnel through. That can happen for real balls, but if you make an electrical circuit in the right way, you can show that. Let's talk about macroscopic variables to make sure we really understand that. A good example is a gas at a high temperature of some material. Everything removes from the surface. The atoms are flying around. Obviously, a very complicated state to describe. If you go before the solidification temperature, it then forms, let's say, a solid, maybe even a crystal. But now, if you want to describe the state of that system, you just describe the center of mass. And that's a much more simpler description of what's going on with the physics of that than when it's in a gas. Same thing for electrons in metal. There's some Fermi statistics you have to worry about, but you can have a think about a gas of electrons. When you cool it down, it turns out the electrons flowing in one direction and electrons flowing in exactly the other direction form these things called Cooper pairs with a net zero momentum, so that each Cooper pair has zero momentum, and then every Cooper pair can interact with every other Cooper pair through some condensation mechanisms with phonons. What's very nice about the superconducting state is there's a free parameter to the state, just like in the solid, having the center of mass being a free parameter called the phase. And if there's a change in phase over distance, that is equivalent to a current flowing through the wire. And as long as that current isn't too big, it's in the superconducting state. If its current's too big, it kind of starts looking like a normal metal. It breaks the Cooper pair. Okay, so you have to keep that. So what we do here is make a superconductor with a weak link, a barrier. Here it's a very thin aluminum oxide. And then from the Josephson effect, the current that flows through it has a maximum value of a critical current, which we can tune for a few microamps in our devices with a sign behavior, the phase difference, has been discussed before. But here, everything is still classical. This phase is a classical variable in normal way that you describe superconducting devices. As we've discussed before, we're interested in the zero voltage state where it looks like a good superconductor. And then if you have too much current through that, it then goes into a normal state, voltage state, rolling down the well. And this transition is determined by going over or through a barrier that we've described here. And that barrier height goes to 0 when I goes to I0. It goes as the 3½ powers as to how close it is to that. Now, from this kind of description, one of the first things we did in the experiment was really clearly write down what the physics is. And that's shown in the 3 formulas here. The important thing is at high temperature, classically, this is just a Boltzmann factor and Arrhenius law, something you study in chemistry and physics all the time. And it's dependent very sensitive on the delta U over KT ratio, okay? Then in the quantum regime, it could tunnel, again given by another formula that I've given here. There's also, we consider the third case because of the quantum noise, delta U over 1/2 h bar megaplasma. We thought that wouldn't happen, but the point is these 3 formulas are very distinct. And if we measure the parameters carefully, we can tell the difference and we can identify what the physics is. Now, I want to talk a little bit about this quantum tunneling. And as journalists talk to me because of the Nobel Prize, whenever I say, well, there's a wave function, it leaks on the barrier, they totally don't understand that. So there's, I think, a little bit more intuitive way to think about it. And that is nature it can be a nervous banker. Okay, and what nature can do is it could lend you some energy, but they're going to want to recall the loan, and bring back the energy a small time later, t, such that the energy times the time is equal to this Planck constant h bar, which Michel talked, is about 10 to the minus 34 in natural units. So if you have to have small delta U's and small delta D's, but then you can still borrow and return the energy. Now, one of the nice things about thinking it that way is if you put in damping and friction, as Michel talked about, you can imagine that because of the friction that goes on during the tunneling event, you're going to have to borrow a little bit more energy to make sure you can overcome that. And that's why in the quantum formula, in the exponent, there's this factor having to do with dissipation. So you can strongly reduce quantum tunneling if you have dissipation, and you have to design your experiment around that. So here's the experiment, and what I'm going to say is when we first did the experiment, it was a total disaster. It didn't work, didn't make any sense. No surprise if you're experimentalists. And we just sat down and tried to understand what was going on. And one of the first things we realized is that microwaves, this is a microwave experiment, right? This is oscillating at about 5 or 10 gigahertz. And that microwaves at that frequency are in fact very sneaky. And you know that because you get cell phone transmission from outside way far away, even inside a building. It can penetrate in some way and do that. So we had to design the experiment to be really good shield for microwaves. And we did that using this particular design. We have the chip here on the right with the cross for the junctions, and then it's connected to what is a coaxial line, which is really well shielded. There's a cap on the end to make sure that that's good. And then furthermore, in that what's coax, we put in copper powder, which is very damping of these microwave radiation because it has a lot of surface area in it. And you can see we go in with the copper powder. We have this SMA connector at the end, which is a really good tight connector. And then the other two barrels on the left-hand side on the picture are further filters to make sure none of this energy goes in. In the center, we have another microwave connector to inject microwaves that you talked about. So the filter here is actually one of the most important things we figured out and measured carefully, and that's how we got the experiment to work. So how do we measure the parameters? This was very important. So on the left, I think we already talked about, we took the device, measured the switching times, switching rates at a variety of currents, okay, so that the frequency is slowly changing there. We put in a fixed frequency here, 4.9 gigahertz, and then you see an enhancement of the rate when the microwave drive of the particle in the well here is at the same frequency, resonant enhancement. Study that all the time in physics. So from the peak of that particular transition, we can get the oscillation frequency of the system, and from its width on the high side, we can get the damping of that. So with that, we have a basic parameter, the oscillation frequency, which we need to know. On the right, we now plot the raw data. This is of the gamma. We normalize that to the plasma frequency over 2 pi. It's the attempt frequency. Take the log, and because of the power law, 1 minus I over I0 to the 3/2 for the delta U, you take to the 2/3. And this is an Arrhenius-like kind of plot, where if your data is good, remember at the beginning it wasn't, but now it's good, it should be on a nice line, which is what we see with the points kind of in the center of the plot. Those particular points, this is really nice. If you extrapolate that back to the 0 on the vertical axis, that then gives you the critical current to the device. That's where delta 0 goes to 0. And you can do that at various temperatures to see that you get a consistent value of I0. You put in corrections to understand that properly. And then the interesting thing, as you get the lower and lower temperatures, it gets steeper and steeper. And then between about 25 and 19 millikelvin, it just doesn't change anymore. And again, that's an indication that you're seeing new physics. So the slope of this is kind of giving you an effective temperature of the device, scaling out the delta U that's in the formula. So this is something we call the escape temperature. And here it's a plot of the escape temperature versus the real temperature, and as described before, T escape equal T at high temperature, because this is all classical physics. That's what you expect. And then as you go to lower temperature, it begins to level off. Now, let me stop here for a second. The fact that it's leveling off doesn't necessarily mean you're seeing quantum tunneling, and that was the big insight we had in the beginning. How do you know it's not other physics? It could be noise getting injected somehow in your system, and that's what's causing you to level off. So you really have to think carefully about what the check experiments are. Okay, so the one check experiment, we already bit the good microwave filtering, and we knew everything there was okay. The second part is we could take the system with the critical current and lower it by putting a magnetic field parallel to the junction. So that brings the critical current down to about 1 microamp. The frequencies of the oscillations are then lower. And then now it's going to be classical, almost always classical, almost all the way down to the end. And those are the open circles. And you see that it goes below. And that kind of proves that we understand what the temperature of the system is good enough. Now, and then the last thing is it levels off. What does it level off to? And that's the little symbol on the left for MQT, and that's the prediction after measuring all the parameters. And you can see within experimental error bars, everything's okay there. So we think that's a really solid way to understand that this is working properly. And we worked along really hard to figure out how to numerically show that. Okay, now I want to talk about energy level quantization. And this slide is for the new students who are learning about quantum mechanics. And the problem is in quantum mechanics, it was first understood, kind of discovered through the Planck radiation law of, infrared spectrum, okay? And there, what happens is you assume that the energy levels are quantized and separated by h bar omega, but then you have to do a bunch of statistical mechanics calculation, which at the time is really kind of murky and mysterious and hard to understand, and then you can reproduce the data, which is really great. However, for a new student, you kind of get overwhelmed here. So what I want to show you is that with our new quantum devices that we can now make, which is kind of a child of all this work, you can directly measure photons. Okay, so this is an experiment I did with Sewu Nam in the late 90s. Unfortunately, he died last year, but the experiment is really great. And what we do is we take a very small piece of superconductor at very low temperature, which has small heat capacity, and you operate it on the superconducting transition, so it's very sensitive, and then you connect it to a quantum limited squid amplifier we talked about before. And now what you can do is you can put a pulse of energy and see really, really small fine energy resolution. So you take what looks like a classical pulse of light, this is a laser light, 1556 nanometers, you make a small pulse of it, so that on average has a certain, there's a certain amount of energy, you attenuate that, and you put it onto the microcalorimeter, okay? And when that absorbs the energy, it turns it into heat, the temperature rises, and then it'll fall over some amount of time going back to equilibrium. Exactly what you expect for a fast thermometer. And on the upper right of my figure here, we'll show some time traces of that, where you see that the temperature goes up, that's the signal, and then it goes down over time. But if you look at it, there are these bands of the temperature profiles. And if you look at the peak and you histogram that, that's the data you have here. So you have discrete peaks in the energy of this pulse. Now, classically, you would expect one energy. But here you see a band of them, and those are all separated by Planck's constant times frequency. And this energy level quantization that you see is exactly what you're assuming in the Planck radiation law, but now you just directly see it coming out of your oscilloscope from a fancy detector where you can measure very, very small energies. And my hope is that future generations can look at this experiment and kind of get a better intuition about how this works. So that's why I'm introducing it here. And then here we have an energy level experiment that we talked about before, where we put on microwaves and we see an enhancement of the escape rate when the microwaves are resonant in a certain way. And this is really great. This is a qualitative way to show you that you have a unique signature of quantum mechanics. That's kind of the fundamental signature with energy level quantization. And that was really great, great to see. When I saw this come up on the oscilloscope, this was like the most exciting part of my graduate student career. So what do we have looking at this? We have a new way to make artificial atoms. Normally we have the periodic table. Now we can look at these electrical circuits. And what I learned here at the Nobel Week is I was looking at the poster for the Economics Prize, and it described about propositional knowledge. And what happens is when you have this kind of knowledge, it's very fundamental knowledge of what you're looking at technologically, it allows you to make discovery after discovery after discovery because you can kind of generalize and really understand what's going on. And what I would say is in this experiment, we tried to go to the basics to really understand this. And because of that, over the last 40 years, everyone in the big field has been able to make huge progress on that. I do want to make a caveat, though, that to make this progress, nature has been very kind to us with stable junctions so that we can do high-quality experiments. but has given us little subtleties at the same time, so a lot of physicists have to be employed to make this all work. So that's a good combination, okay. So Clay, right after that, we did a very nice experiment where we actually measured this tunneling time, okay, and how do we do that? Well, using the ball analogy, we make a ball that's squishy, okay, and that has some time dynamics that we can tune, and then we look what happens to the tunneling as we change the ball. Now, in this case, we have a junction at the end of what's called a coplanar waveguide. It's much more sophisticated engineering. Right next to the junction is something with a wave impedance, a wave resistance of 72 ohms. And then some distance away, we have a kind of a short on it that has a lower resistance that gives you more dissipation. And then we connect that with a string all the way up to room temperature so we can change the distance. Now, as we look at the escape rate on the right, at high temperature, is given by delta U over KT. It's more or less flat. But at low temperature, then you get a big change in the rate or in the time, as shown by the finger. At short times, it's looking at the short with a lot of dissipation on it, and that gives you longer tunneling times. And then when it's long, you aren't seeing that dissipation anymore. You're seeing the 72 ohms, and it goes down to different. And then in between, it kind of goes up and down. And what's happening is, at this tunneling time, in this case about 30 picosecond delay, what's happening is the system is tunneling before that tunneling event has a chance to go down to the line, interact with the M, and come back and interfere with itself. So this characteristic time here is telling you this particular tunneling time. It's a real physical quantity. I think it's very nice with an artificial atom you can measure that. I want to next talk about something we did at UC Santa Barbara in 2008 and 2009 with Andrew Cleland here is in the audience. We were making qubits at that point, and we connected a qubit to what's these resonator circuits. And what we did in this particular circuit is we can calibrate up the qubit. We can, on the bottom left curve, we can put the qubit off resonant, so it's not talking to the resonator, on resonant, having it talk, calibrate that up so that we can controllably transfer photons from the qubit to the resonator. And what's very nice here is we're able to generate these very complex states. For example, 0 plus 5 or 0 plus I3 plus 6. And we do this using the very beautiful protocol of Law and Eberle. But basically, by doing these two calibrations, but now doing a series of 10 or 12 pulses that interact everything together, from a simple calibration, we could then create a much more complicated state. And you see in the top here in the theory, the experiment is very much similar. This is a pseudo probability distribution called the Wigner distribution, which tells you about the quantum state. And reason I'm showing you this is we went from a simple calibration to a complex state generation. And at that experiment, I really had much more confidence that we can build a complicated quantum computer sequence and get it to work. So it gave me a lot of confidence we were on the right track. And then finally, before I summarize, this is the quantum supremacy experiment I did at Google, where we showed that with the 53 qubit, we can make a very complicated sequence with thousands of total gates calibrated upright and show that the results we get is equivalent to what you expect from quantum mechanics. And what was interesting here is the power of this circuit comes from using a very large computational space. It's something physicists call Hilbert spaces, which is about 2 to the 53, so it's about 10 to the 16 states. So, you know, kind of in analogy to my thesis experiment, this was showing that macroscopic quantum computation also based quantum mechanics. So we've pushed the knowledge of quantum mechanics even further. And it's nice. Other groups have even extended this even further. And, you know, because we've done that, we think it should be possible to build a powerful quantum computer. We just have to figure out what are the useful algorithms and fit that in right. So here's a nice summary of graduate students in 1985, what we were building. Still a good microwave experiment, but then the kind of chips we're building in 2019, and the whole field has been developing this in a very sophisticated way. It's great, and really excited for the future. What I'm trying to do, and my thesis, is going from 2019 to, let's say, 10 years from now, 5-10 years from now, to build a useful quantum computer. We're going to have to make a technological jump in fabrication that I believe is going to be just as big as from 85 to, say, 2019. However, I think because we can now use the semiconductor industry to do that and make it in a more reliable way, I don't think it's going to take 35 years to get there. I think we can do it much faster. So that's what I'm trying to do with my company. So in the final slide here, I just want to summarize that. And as I said in the beginning, I wanted to study these devices to kind of learn about quantum mechanics, and I would say intuitively understand how quantum mechanics worked. And I would say that's what's happened in my career, and it's been a real pleasure to understand that. And just to review that, we have this nice experiment that shows photons, that shows energy level quantization directly, which is really nice. We now can understand that tunneling traversal time. We have these photon generators, complex generators, and then the quantum supremacy experiment, where I think the remarkable thing that I found there, this is a prediction from quantum mechanics, but experimentally, is that although quantum mechanics isn't perfect and you get errors into it, if you just measure the single and duplicate errors and then measure the errors of the whole complex system, it's given, the relation is given by high school probability statistics. And I think it's just amazing that quantum mechanics works in this way, where you can get complex calculations out of it, but on the other hand, the imperfections of it can be understood in a more simple way. So with that, thank you for your attention. It's been a real pleasure to talk to you about my journey. Thank you.
Very nice. Very nice. So thank you, Professor Martinis. This summarizes the 3 Nobel presentations for the Physics Prize, and let us all thank the speakers one final time. Oh, please come on stage. On stage.